Hello, my name is Koyanagi. I'm a PhD student at WPI-IIIS, University of Tsukuba, Japan. Our lab recently developed an AI-based automatic sleep stage-specific intervention system. Here I am going to introduce its performance and example of the application for sleep stage-specific optogenetics. Sleep stages are mainly divided into two stages, non-REM and REM sleep. The sleep stages can be classified by the characteristic waveform of electroencephalogram (EEG). For example, in REM sleep, low amplitude uniform 6 to 9 oscillation called theta wave is observed. To understand the function of sleep or its regulation mechanisms, sleep stage-specific intervention has been carried out in sleep research. However, number of studies is limited due to the complexity of the experimental procedure. If the machine can classify the sleep stages accurately and precisely, the experiments are much more smooth and it allows to examine the long-term effect of sleep stage-specific intervention. In collaboration with Dr. Tezuka in our university, we developed an AI model UTSNL, Universal Time Series Network connected with LSTM. The point of the network structure is that UTNSL uses one single EEG channel and accumulates short historical information for the sleep stage prediction from 10-second time window of the EEG wave. To assess the performance of UTSNL2 in living mice, we performed the following. First, UTSNL2, the derivative of UTSNL, was implemented into a sleep recording system. The left panel shows the user interface. Second, EEG-EMG was implemented in 4 mice and the signal were recorded for 22 hours for 3 days with online sleep staging. Then the EEG signal were analyzed by human experts in offline and the classified sleep stages were compared. For the evaluation, we compared the sleep classification by UTSNL and that of by human expert ground truth (GT). First, I compared the sleep architectures, especially for total amount, episode count, mean duration, and FFT power density ratio. The gray bars indicate ground truth, and the pink bars are UTSNL2. This group shows similar sleep architecture overall. The hypnogram in ground truth and UTSNL2 were almost identical. Next, scoring the UTSNL2 were carried out by categorizing the judges into true positive, true negative, false positive, false negative. From these categories, sensitivity, specificity, accuracy, and precision was calculated. I also measured F1 score, MCC, kappa statistics. The upper right panel shows the confusion matrix. The bottom panel shows the scores in each sleep stage. In average, UTSNL2 shows 81% sensitivity and 91% precision for REM sleep. I particularly mention about REM sleep. It is because generally REM sleep amount is less and the detection is difficult. One of the important parameters for the real-time sleep staging is the time resolution, considering the short duration of REM sleep. Using a new teacher dataset, we developed UTSNL2 4-second for staging 4-second time window. We assessed the performance in 5-fold cross-validation test. The result is shown in the confusion matrix and the bottom graph. In all the validation, wake and non-REM sleep performed more than 90% scores. REM sleep scores were more than 84%. These results indicate that UTSNL2 4-second works as well as the original 10-second version. Finally, we examined the performance of UTSNL2 for REM sleep-specific optogenetic manipulation. As shown in the bottom graph, UTSNL2 performed consistent scores among the mice, and the scores are more than 80%. This indicates that manual optogenetic manipulation can alternate with UTSNL2. Again, I am Koyanagi. Thank you very much for listening to my presentation. Special thanks to the people in this picture and the funding agencies that support this work.